Hi, in this video we'll be going into a deep dive of some properties of Sieve that can be leveraged to calculate some more properties of numbers. So Sieve in general can calculate a lot of different properties of numbers provided the property has some relation with factorization or divisors of the number, right? So let's talk about two different properties, S0, which is, let's say, the number of divisors of a particular number, and S1, let's say, is the sum of divisors of all the numbers, right? So if, let's say, you want to calculate the number of divisors for all the numbers in the range 1 to n, where n is up to 10 to the power 6, okay, or let's say you want to find the sum of divisors for all numbers in range 1 to n, so you can do this very easily with Sieve. Now, why these properties are like possible to be done using Sieve? Because you can calculate these properties using the factorizations of numbers. Okay, so let's suppose there is some number which has, like, let's say some n is equal to p1 to the power alpha 1, p2 to the power alpha 2, and so on up to pn to the power alpha n. Okay, so for this, the number of divisors including 1 and as n itself can be found out using the formula 1 plus, let's see, 1 plus alpha 1, 1 plus alpha 2, so on up to 1 plus alpha n. Okay. Why is this? Because for every prime you have 1 plus alpha 1 number of choices, right? 0, 1, 2, 3, 4 up to alpha 1. How many primes do you take in that particular divisor? And they are independent on each prime, so you can find this out too, and it comes out to be this formula, right? Similarly, for sum of divisors, if we have this particular factorization available, you can find out the sum of divisor to be equal to p1 to the power alpha plus 1 minus 1 divided by p1 minus 1. Okay, then so on with the terms of p2 to the power alpha 2 plus 1 minus 1 by p2 minus 1, and so on, right? You can find out the formula for sum of divisors of a number using this if you have the prime factorization, right? Also, you can run a divisor loop. So instead of Sieve of Eratosthenes, you can, like, for every number I, you can just add I to all of its multiple and you can calculate divisors of every other number, right? Similarly, for if you want number of divisors, so for every number I, what you can do is you can loop over its multiple and you can just increment the count of its divisor. So at the end, for all the numbers, it will calculate the divisors. Okay, so this is the another way in which you can calculate the number of divisors. So that would be n log n, because if we run on all the numbers, like not only on primes, then it is n log n. If we run only on primes, it's n log n. Okay, so let's talk about a example of some property of numbers that we can calculate using, let's say, Sieve. Okay, so let's say we have a function fx which is given, which counts the number of numbers a in the range 1 to x such that GCD of x comma a is 1, right? So it basically finds out the number of numbers in the range 1 to x which are co-prime to the numbers. Okay, we want to find out how many such numbers are co-prime to all the numbers in the range 1 to 10 to the power 6. Okay. Now, if you talk about, let's say, for 6, we know, so this would be divisible by, so so for, if you take it with 5, if you take it with 3, if you take with 2, if you take with 1, these would be like co-primes to all of these numbers, right? Like, so if you take with any one of them, it's just like it's working fine. Also, we don't consider 1 for these numbers, so we would be skipping 1 for out of these, because 1 is trivially, like, GCD would be 1, so we would be just counting these 3. Okay, okay, so oh, 2 would not be there as well, because if you take 2 and 3, so if we want to calculate the numbers which are co-prime, that would be nothing but 1, 2 will not be there, 3 will not be there, 4 will not be there, 5 will be there, and 6 will not be there, right? So 1, 5 would be there. Make sense? So we keep 1 and 5 as the count of divisor, let's say. Okay, so we are including 1 in this particular set, so 1 would be there because it follows this property. Okay. So we want to find out the number of such numbers for every number. So we found out this number, so this would be 2. Okay, so we found out this number for 6. We want to calculate it for all numbers in the range 1 to 10 to the power 6. How do we do this? So try to pause the video and think about this particular problem once you have like thought about it, and then you can continue and watch the solution. Okay, so let's understand the count that we are trying to build up. Okay, so let's say some number is there which has, like, let's say a prime p1 with p1 square and p2 cube. Like, let's say this is the prime factorization of that number. Okay, we don't know what p1 p2 is, but that doesn't matter. Okay, so now we know if this is the case, then there in the range 1 to x, if we take any multiple of p1, okay, that is going to be a problem. Why? Because then GCD would be p1 or something more than that, right? So we cannot take any multiples of p1. So we would be looking into inclusion exclusion a bit. So let's say we can take all the numbers in the range 1 to x, that is x, minus we subtract out those which are divisible by p1. Now note that this is the formula when we want to count the number of multiples of p1 from 1 to x. However, x is perfectly divisible by p1 because we know that p1 is in the prime factorization, so we don't need the floor function over here. So we can simply write this as x by p1. We also subtract x by p2 with a similar reason, because p2 should also not come in the prime, like in the number that we are there. However, we would have counted some numbers multiple number of times which are divisible by both p1 and p2, so we would add that back, right? Make sense? So this is just inclusion exclusion into place. These powers don't make any sense because anyways, like if it is not 1, if the GCD is not 1, then we already discard it, right? So powers don't make any sense over here. So once we have this, if we just quickly look into the formula, like just transform some of the things over here and there, this is going to be 1 by 1 minus p1, and this is going to be 1 minus 1 by p2. Okay, now if you look into this, this is nothing but like a formula, like the x multiplied by 1 minus 1 by p1, that is one of the prime factors, 1 by 1 minus p2, that is another prime factor, and this is like working for this particular x, right? So if we now talk about some general number, this general prime factorization, this, we can find out that f of x would be equal to x multiplied by 1 minus 1 by p1, 1 minus 1 by p2, and so on to 1 minus 1 by pk. Okay, this should be coming up. So we are not writing all the terms, but the logic would remain similar. Okay, so this particular number comes up. So now let's understand that this particular number that we are counting right now is a special number in number theory. Okay, so number of co-primes which are less than equal to a x and greater than equal to 1, number of co-primes to x from x to 1, 1 to x, is called something called totient of x. Okay, how many numbers are co-prime from x? This is called totient of x. Okay, and this is a closed form formula for totient of x. Okay. So in this problem, we are basically trying to calculate totient of x for any number x in the range 1 to 10 to the power 6. Okay, so now we want to calculate this number. So what we'll be doing is, so this is phi. So initially we initialize all the numbers with phi of I equal to I. Okay, now we can obviously run a separate loop and find out which numbers are prime, right? We can very easily do that. Okay, which numbers are prime, that is a separate segmented sieve, separate normal sieve that we have to run for 1 to n, and that will find all the numbers if it's a prime or not in n log n, right? Now in the second part, what we can do is we can run this separate loop where if it's a prime, we loop over its multiples. Okay, we loop over all its multiples and we subtract this particular term, that phi of j minus equal to phi of j by I. So what is the thing that we are doing over here? So let's suppose this currently the phi of j values x, it is getting subtracted by x by I. So this is nothing but making it 1 by 1 minus I, right? And which is correct because I is one of the new prime factors of this particular j, right? So we have to subtract I from 1 by 1 minus I, 1 minus 1 by I from j's phi. So that's what we are doing right over here, and this will create the phi for all the numbers that are in the multiples of I. So it will add the contribution of 1 minus 1 by I to all the multiples which contains I, right? Similarly for other primes as well. So this will actually calculate the totient value for all the numbers in the range 1 to the power 6 up to n. Make sense? So this is how you can calculate some property of numbers using Sieve. Now let's talk a bit more about the totient of n. So there is some properties that you can keep hold on, and like these would help you. So for any totient, if totient of any prime is equal to p minus 1, okay, this is something you can keep a note of, because this is nothing but p multiplied by 1 minus 1 by p. That would be all right from the closed form formula. This is nothing but p minus 1. Now p to the power k would be p to the power k. For p to the power k, the totient is p to the power k minus p to the power k minus 1, because p to the power k multiplied by 1 minus 1 by p to the power k, pk, this would be p to the power k minus p to the power k, right? This is all. Now this is an interesting property, that totient of any two numbers is equal to totient of first number multiplied totient of second number if GCD of a and b are 1, like if they are co-prime. So if there is no prime common to a and b, we can split the totient into different numbers, and which is quite true, right? Because if you think about this, if you think about, let's say, what is p1 multiplied by some p1 multiplied by p2, this is nothing but p minus 1, p1 minus 1 multiplied by p2 minus 2 from this left hand side, and this is nothing but p1 p2 taken common out, sorry, this is 1 minus 1 by p1 and 1 minus 1 by p2. So this is also like the closed form formula of this, right? So this is correct, and this particular property is called multiplicative property of some function, okay? So any function which is multiplicative can be very easily calculated in sieves, okay? So this is something you can know of, like totient follows a multiplicative property. So if like there are two numbers and you need to find the product's totient, and there are no common, like the GCD is 1 or there is no common prime between them, so you can like split the totient if you want, okay? So that's all for this video. See you in the next one.